engineering the industrial revolution of glass. By the mid-20th century, the industrialized world was constructing its future through a lens of increasing transparency. Yet the material at the center of this architectural and automotive revolution, glass, remained tethered to manufacturing processes that were archaic, energy-intensive, and physically limited. Before the 1950s, the global glass industry was bifurcated into two distinct and imperfect lineages: sheet glass and plate glass. Sheet glass, produced by drawing molten glass vertically through cooling towers using methods such as the Fourcault or Colburn processes, was affordable and capable of mass production. However, it was optically distorted, riddled with roller waves and ripples that warped the view of the post-war world, making it unsuitable for high-quality applications like automotive windshields or luxury storefronts. Conversely, plate glass offered the optical clarity required for these high-end applications, but achieving it came at a staggering economic and energetic cost. The plate process involved casting molten glass onto large tables, rolling it flat, and then mechanically grinding and polishing both surfaces to remove surface imperfections. This grinding and polishing phase consumed vast amounts of energy, required massive capital investment in machinery, and generated mountains of waste material, with up to 20% of the glass thickness being ground away to achieve parallelism. The era spanning the 1950s through the late 1990s represents the most significant paradigm shift in the history of glassmaking since the invention of the blowpipe in Roman antiquity. This period did not merely refine existing methods, it obliterated them in favor of a new physics of production. It began with the invention of the float glass process by Sir Alastair Pilkington, a breakthrough that utilized the fundamental laws of fluid dynamics and surface tension to achieve optical perfection without mechanical intervention. This innovation alone standardized the substrate of the modern world, but it was the subsequent advancements in secondary processing that truly defined the era. As the float process scaled to meet global demand, engineers and chemists began to manipulate the ribbon itself. They developed magnetron sputtering vacuum deposition, or MSVD, to cloak buildings in microscopically thin metallic veils, allowing skyscrapers to rise in climates previously deemed uninhabitable for glass facades due to thermal load. They mastered the thermodynamics of tempering and the chemistry of lamination, transforming brittle sheets into ballistic shields capable of stopping military-grade projectiles, thereby reshaping the security landscape for heads of state and military convoys. Simultaneously, the chemical composition of the glass was rigorously standardized, with precise additives introduced to control color and clarity to an atomic degree. The first part of this review conducts an exhaustive deep dive into this transformative half-century. It explores the production mechanics of the float process, the structural engineering of skyscraper glazing, the chemical evolution of safety glass, and the standardization of the material that encases our modern lives. It is a chronicle of how a viscous, supercooled liquid was engineered into a structural, thermal, and ballistic barrier, defining the aesthetic and functional parameters of the late 20th century. Float glass paradigm shift. The transition from plate and sheet glass to float glass was not merely an upgrade in machinery, it was a fundamental reimagining of how liquid glass behaves under gravity and surface tension. The invention of the float process in 1952 by Sir Alastair Pilkington and its subsequent commercialization in 1959 hinged on the counterintuitive realization that the only material smooth enough to mold perfectly flat glass was another liquid. The float process is a continuous, integrated manufacturing sequence that transforms raw mineral earth into an optically perfect ribbon of glass. The line itself, often stretching nearly half a kilometer in length, operates non-stop for campaigns lasting 10 to 15 years, producing approximately 6,000 kilometers of glass annually. The engineering marvel lies in the precise thermal and mechanical control exerted over the glass as it transitions from a low-viscosity liquid to a rigid solid. The process begins in the melting furnace, a colossal refractory structure holding up to 2,000 tons of molten glass. Here, raw materials, primarily silica sand, soda ash, limestone, dolomite, and salt cake, are subjected to temperatures exceeding 1,500 degrees Celsius. The furnace is not a static pot, but a complex flow system where melting, refining, and homogenizing occur in distinct zones. The refining zone is critical. It is here that bubbles are eliminated and the chemical composition is stabilized to ensure uniformity. The molten glass, now at approximately 1,100 degrees Celsius, flows gently over a refractory spout or lip onto the float bath. The heart of the paradigm shift is the float bath. The molten glass pours onto a vast, shallow pool of molten tin. Tin was selected for this role due to its specific physical properties. It remains liquid over a wide range of temperature, 232 degrees Celsius to 2,270 degrees Celsius, has a higher density than glass, preventing the glass from sinking, and has a high surface tension that encourages the formation of a smooth interface. As the glass flows onto the tin, it surrenders to the forces of gravity and surface tension. In the absence of external forces, the glass naturally spreads to an equilibrium thickness of approximately 6.9 millimeters, often cited as roughly 7 millimeters or 0.27 inches. At this thickness, the gravitational force pulling the glass down is perfectly balanced by the surface tension forces holding it together. This natural equilibrium was the initial limitation of the process, but engineers soon developed mechanical interventions to manipulate this thickness. To produce glass thinner than 6.9 millimeters, essential for automotive applications, top rollers or fenders grip the edges of the cooling ribbon and stretch it longitudinally and laterally, increasing the speed at which it is drawn off. Conversely, to produce thicker glass for architectural or security use, the spread of the ribbon is restricted by non-wetting barriers, allowing the glass to pile up to thicknesses as great as 25 millimeters. The environment within the float bath must be strictly controlled. Molten tin is highly reactive with oxygen, and any oxidation or dross on the surface of the tin can adhere to the glass, causing defects known as bloom or tin pickup. To prevent this, the entire bath is enclosed in a gas-tight shell containing a slightly positive pressure atmosphere of nitrogen and hydrogen, typically 95% nitrogen and 5% hydrogen. The hydrogen acts as a scavenger, reacting with any stray oxygen to form water vapor, which is vented away, ensuring the tin retains a mirror-like oxide-free surface. A critical but often overlooked aspect of the float process is the fluid dynamics at the point where the glass meets the tin, known as the wetback flow. When the molten glass pours over the refractory lip, it does not simply slide forward. The complex interaction of viscosity and surface tension creates a backward flow of glass underneath the spout lip before it turns outward and forward to form the edges of the ribbon. This wetback flow is essential for stabilizing the ribbon and ensuring that the optical quality extends across the width of the glass. The tin bath itself is also not static. The movement of the hot glass ribbon induces convection currents within the molten tin. Hot tin is dragged forward by the glass, while cooler tin flows backward along the bottom of the bath. Managing these thermal currents is vital, as temperature differentials can cause distortions in the cooling glass ribbon. This wetback flow phenomenon is heavily dependent on the mass flow rate and the viscosity of the glass at the delivery temperature. If the glass spreads too aggressively or the flow is too turbulent, it can lead to entrapment of gas bubbles or the entrainment of tin oxide dross into the bottom surface of the glass. Numerical modeling developed in later decades, particularly the work on multi-phase flows, confirmed that maintaining a stable wetback region is crucial for the formation of the onion, the spreading mass of glass at the entry of the bath. The stability of this flow dictates the edge quality and the uniformity of the final ribbon. If the wetback flow is disturbed, it can lead to optical distortions known as reams or chords, which persist in the final product. As the glass ribbon traverses the tin bath, its temperature is gradually reduced from 1100 degrees Celsius to approximately 600 degrees Celsius. At this exit temperature, the glass is rigid enough to be lifted off the tin without marking the underside rollers, but soft enough to crack if cooled too quickly. The ribbon is lifted from the tin bath into the annealing leer, a long temperature-controlled kiln. The leer is designed to cool the glass slowly to relieve internal stresses. If the glass were cooled instantly, quenched at this stage, the surface would contract rapidly while the core remained hot, locking in tension that would make the glass impossible to cut. The leer carefully manages the cooling rate through the critical annealing range, roughly 540 degrees Celsius to 470 degrees Celsius for soda-lime glass. This controlled cooling ensures that the glass emerges with a fire polish, a surface finish comparable to the undisturbed surface of a liquid, requiring no further grinding or polishing. This elimination of secondary finishing was the economic engine of the revolution, reducing production costs and increasing throughput to over 6,000 tons per week per plant. The leer itself is divided into multiple zones, often labeled A, B, C, D, etc., to precisely manage the cooling curve. Zone A typically brings the glass to a uniform temperature, while Zone B manages the critical transition through the annealing point where stress relaxation occurs. Modern leers utilize forced air convection and electric heating elements to ensure temperature uniformity across the entire width of the ribbon, which can be up to 3.2 meters wide. This uniformity is essential for automatic cutting. If the glass has residual stress, the cutting wheel will not produce a clean score, leading to jagged breaks and production losses. Architectural glass scaling, the rise of the monolith. The standardization of the float process in the 1960s and 1970s coincided with and enabled a dramatic shift in global architecture. The International style and late modernist movements demanded facades that were dematerialized, sheer, and transparent. The production of jumbo glass sizes, typically 3.21 meters by 6.00 meters, allowed architects to wrap skyscrapers in uninterrupted skins of glass. However, these massive panes introduced severe thermal penalties. A building clad entirely in clear float glass effectively became a greenhouse, trapping solar heat and necessitating massive HVAC systems. The solution lay in the development of advanced coatings. While early coatings were applied using pyrolytic methods, chemical vapor deposition, or CVD, directly on the float line while the glass was hot, these hard coats were limited in performance and variety. The true breakthrough for high-performance architectural glass was the maturation of magnetron sputtering vacuum deposition, also known as soft coat technology, in the late 1970s and early 1980s. MSVD is an offline process performed in a massive vacuum chamber. The glass sheets are conveyed through a series of compartments where high-voltage electrical fields create a plasma from an inert gas, typically argon. This plasma bombards a target material, such as silver, titanium, or stainless steel, ejecting atoms from the target, which then deposit onto the glass surface. The engineering triumph of MSVD was the ability to deposit multi-layered stacks of materials with atomic precision. A typical high-performance, low-E stack developed in this era consists of a base dielectric layer to adhere to the glass, a seed layer, a functional layer of pure silver, which reflects infrared radiation, a barrier layer to protect the silver, and a top dielectric layer for anti-reflection and protection. The silver layer is the functional engine. It is transparent to visible light, but acts as a mirror to long-wave infrared heat. By the 1990s, the technology had advanced to allow double silver and eventually triple silver stacks. These complex coatings, containing 12 or more distinct microscopic layers, allowed for the decoupling of light and heat. A skyscraper could now have a glass facade that transmitted 70% of visible daylight while rejecting over 50% of the total solar heat energy, a feat impossible with the simple metallic coatings of the 1960s. This technology was pivotal in the construction of the super-tall towers that came to define the skylines of the late 20th century. The vacuum chambers required for this process are engineering marvels in themselves. They must maintain a high vacuum, typically in the range of 10 to the -6th torr, while continuously processing massive sheets of glass. The entry and exit locks use a series of pumped chambers to transition the glass from atmospheric pressure to high vacuum without breaking the seal of the main process chamber. The cathodes, which hold the target materials, evolved from planar designs to rotatable CMAG cathodes in the late 1980s. Rotatable cathodes provided better target utilization and allowed for longer production runs between maintenance cycles, a critical factor in making these high-performance coatings economically viable for mass-market construction. As glass panes grew larger and coatings became more sophisticated, the method of attachment also evolved. The 1970s and 1980s saw the transition from captured glazing, where glass was held on all four edges by aluminum frames, to structural silicone glazing, SSG. In SSG systems, the glass is bonded to the internal frame using high-strength structural silicone sealants, eliminating external metal caps and creating a flush, continuous glass aesthetic. This transition required a rigorous re-evaluation of wind load engineering. Engineers could no longer rely on the mechanical interlock of a metal bezel. Instead, the adhesion of the silicone to the glass and the tensile strength of the sealant became the primary load path for transferring wind forces, which can exceed hundreds of pounds per square foot on the upper floors of a skyscraper, from the glass to the building structure. The iconic towers like the Willis Tower, formerly Sears Tower, completed 1974, pushed these limits. The Sears Tower utilizes bronze-tinted float glass to reduce glare and solar heat gain. The glass panels on the lower floors are significantly thicker, often exceeding 1/2 inch, to withstand the immense wind pressures generated by the Venturi effect of the Chicago streets. The building's design acknowledges that glass is flexible. Under high wind loads, the large panes deflect, bow significantly. The glazing system must accommodate this movement without placing stress on the glass edges, which could lead to breakage. The ledge attraction added later to the Willis Tower, which features retractable glass boxes extending from the 103rd floor, utilizes a layup of 3 layers of 1/2 inch thick glass laminated together, capable of supporting 5 tons of load, demonstrating the extreme structural capabilities of modern laminated glass. Similarly, the World Trade Center towers, completed 1973, utilized narrow vertical glass panes, approximately 18 inches wide, fitting between the dense steel exterior columns. These panes were tempered to resist wind loads and thermal stress. The engineering of these facades required extensive wind tunnel testing to predict the negative pressures, or suction, that occur on the leeward side of the building and at the corners, which can be double the pressure on the windward face. Foundations of safety and armored glass. Parallel to the aesthetic expansion of glass was its transformation into a safety material. The fragility of annealed glass, breaking into deadly jagged shards, was unacceptable for the automotive and security sectors. The 1950s through the 1990s saw the industrial maturity of two critical processes: tempering and lamination. Tempering, or toughening, creates a stress profile within the glass that drastically increases its strength and changes its breakage mode. The process involves heating a cut-to-size pane of float glass to approximately 620 degrees Celsius to 650 degrees Celsius past its transition temperature, where it becomes plastic but does not melt. The glass is then rapidly quenched with blasts of cold air. The mechanics of this quenching are precise. The outer surfaces of the glass cool and solidify almost instantly, while the inner core remains hot and plastic. As the core slowly cools and contracts, it pulls on the already rigid outer surfaces, placing the surface into a state of permanent high compression and the core into compensating tension. It is this compressive surface layer that gives tempered glass its strength. For a crack to propagate, it must first overcome this compressive force. When the glass does break, the release of the stored tensile energy in the core causes the entire pane to disintegrate instantaneously into small, blunt cubes, dicing rather than long shards. By the 1970s, advancements in furnace technology allowed for the tempering of thinner glass down to 3 millimeters or less, and the handling of larger sizes, making it the standard for safety glazing in sliding doors, shower enclosures, and side windows of automobiles. The stress profile must be carefully balanced. If the tension in the core is too high, the glass can spontaneously explode due to minor surface damage or inclusions like nickel sulfide. Conversely, if the compression is too low, the glass will not meet safety standards for brake patterns. This led to the development of heat soaking, a destructive test where tempered glass is reheated to accelerate the phase change of any nickel sulfide inclusions, causing defective panes to break in the factory rather than on the building. While tempering addressed strength and safe breakage, lamination addressed retention and penetration resistance. Laminated glass consists of two or more plies of glass bonded together with a polymeric interlayer. The industry standard interlayer that emerged dominant in this era was polyvinyl butyryl, PVB. First developed in the late 1920s and refined through the mid-century, PVB is a resin known for its optical clarity, tough elasticity, and excellent adhesion to glass. The manufacturing process involves assembling a sandwich of glass PVB glass and subjecting it to heat and pressure in an autoclave. This process removes air bubbles and fuses the layers into a monolithic unit. The key mechanical property of PVB is its elongation. Upon impact, the glass plies may shatter, but the PVB interlayer stretches, absorbing the impact energy and holding the glass fragments in place. This prevents the projectile from penetrating and keeps the occupants inside the vehicle or building from being ejected or lacerated. During the 1960s, the adhesion of PVB to glass was significantly improved through chemical modifications to the resin, ensuring consistent impact performance over a wide range of temperatures and humidity levels. This was crucial for the automotive industry, as windshields needed to perform equally well in the freezing winters of Scandinavia and the scorching summers of the Middle East. By 1966, the thickness of the PVB interlayer for automotive windshields was standardized at 0.76 millimeters or 30 mil to meet the new high-penetration resistance standards, which significantly reduced laceration injuries in car accidents. The convergence of tempering and lamination technology laid the groundwork for the first generation of reliable bullet-resistant glass, BRG, for military and executive protection. In the post-World War II era, early bulletproof glass was simply excessively thick stacks of laminated plate glass, often resulting in heavy, green-tinted blocks that distorted vision and delaminated over time. The 1970s and 1980s introduced a more sophisticated approach, the use of glass-clad polycarbonate. This composite material leveraged the hardness of glass to deform and strip the jacket from a bullet, and the high-impact toughness of polycarbonate to catch the bullet and absorb its kinetic energy. A typical layup for a high-security vehicle, such as those used by heads of state or in the Mercedes-Benz Guard or BMW high-security series, might involve a strike face of hard, chemically or thermally strengthened glass to flatten the projectile, followed by energy absorption layers of multiple glass plies interleaved with PVB or polyurethane, and finally a spall shield. The spall shield was a critical innovation. In older all-glass designs, the impact of a bullet could cause the inner surface of the glass to shatter and spray high-velocity glass shrapnel into the vehicle cabin, injuring occupants even if the bullet was stopped. The polycarbonate inner layer eliminated this by flexing and containing the glass fragments. By the 1990s, these layups were standardized under ratings such as the European CEN 1063, levels BR1 through BR7. A level BR6 or BR7 executive limousine required glass thicknesses ranging from 40 mm to over 70 mm, capable of stopping multiple rounds from high-powered military rifles like the 7.62 by 51 mm NATO round. The engineering challenge was not just stopping the bullet, but maintaining optical clarity through inches of material, which required the use of high-purity, low-iron glass to prevent the Coke bottle green effect that would otherwise render the glass opaque at such thicknesses. Vehicles like the Mercedes-Benz W126, produced 1979 to 1991, and the subsequent W140 S-Guard were pioneers in integrating these heavy glass modules into the vehicle chassis. The W140 Guard, for instance, featured windows that were essentially transparent armor blocks, requiring hydraulic window lifts and reinforced door hinges to handle the immense weight. The glass was designed with a stepped edge to fit into the door frame, ensuring that there were no ballistic gaps where a bullet could angle between the glass and the steel armor of the door. Chemical composition standards, the Soda-Lime-Silica recipe. Beneath the mechanical innovations of the float process and the sputtering chambers lay the fundamental chemistry of the glass itself. Throughout the 1950s to 1990s, the recipe for commercial soda-lime-silica glass was rigorously standardized to ensure compatibility with the continuous float process and to meet the demands of secondary processing. The vast majority of industrial glass produced during this period adhered to a narrow compositional range, optimized for durability, melting efficiency, and cost. The primary network former is silica, SiO2, derived from sand, constituting roughly 70 to 74% of the backs by weight. Pure silica has an impractically high melting point, over 1700 degrees Celsius, so soda ash, Na2CO3, is added as a flux to provide sodium oxide, Na2O, typically 12 to 16%, which disrupts the silica network and lowers the melting temperature to manageable levels. However, sodium makes the glass water-soluble, water glass. To restore chemical durability, limestone, CaCO3, and dolomite, CaMgCO3-2, are added to provide calcium oxide, CaO, 10 to 14%, and magnesium oxide, MgO, 0 to 5%. Alumina, Al2O3, is also included, 1 to 2%, to improve weathering resistance and control viscosity. This soda-lime-silica formulation became the global standard for float glass. Standardization was driven by the need for predictable viscosity curves. The float process demands that the glass viscosity be precisely controlled at specific temperatures, low enough to refine in the furnace, log 2 poise, fluid enough to spread on the tin bath, log 4 poise, and stiff enough to be lifted off at the exit, log 9 poise. Any deviation in the chemical ratio alters these viscosity points, potentially causing the ribbon to break or distort. For instance, increasing the magnesia content can lower the liquidus temperature, the temperature at which crystals begin to form, which reduces the risk of devitrification, crystallization, in the cooler parts of the float bath. While the base recipe provided the structure, specific additives were used to manipulate the optical properties. The greatest enemy of clear architectural glass is iron oxide, Fe2O3, a natural impurity in sand that imparts a green tint. For standard clear glass, manufacturers accepted a small iron content, roughly 0.1%. However, as glass became thicker for security and architectural applications, this green tint became objectionable. To counter this, physical decolorizers were used. Selenium, which produces a pink/red hue, and cobalt, which produces a blue hue, were added in minute quantities. These colors are complementary to the green of the iron. When combined, they neutralize the green, resulting in a neutral gray that the human eye perceives as clear or white, even with a slight reduction in total light transmission. For low iron or extra clear glass, which became increasingly important in the 1990s for solar panels and high-end architecture, the strategy shifted from masking the iron to eliminating it. This required sourcing exceptionally pure sands with iron levels below 0.015%, a logistical and geological constraint that made such glass a premium product. This glass appears practically colorless, even when viewed from the edge. To ensure the glass was free of bubbles, seeds, and blisters, chemical fining agents were essential. In the mid-20th century, arsenic trioxide was a common fining agent, but environmental concerns and toxicity led to a shift towards sodium sulfate. In the furnace, sodium sulfate decomposes to release sulfur dioxide, SO2, and oxygen. These large gas bubbles sweep through the molten glass, collecting smaller microbubbles and carrying them to the surface. The chemistry of sulfate fining is delicate. It requires precise control of the furnace's redox, reduction-oxidation, state, often managed by the addition of carbon, anthracite, to the batch. If the batch is too reducing, the sulfate can form amber chromophores, iron sulfide, turning the glass brown. If it is too oxidizing, the fining action is inefficient and bubbles remain. Automation and quality control. The Industrial Revolution of glass was also a digital revolution. As float lines increased in speed and width, manual inspection became impossible. The 1980s saw the integration of laser scanning technologies and direct digital control (DCS) systems into the glass plant. Laser inspection systems utilized retro-reflective scanning techniques to detect defects as small as 0.1 millimeters on a ribbon moving at 20 meters per minute. These systems used a rotating polygon mirror to sweep a laser beam across the width of the glass. Any defect, such as a bubble, stone, or tin drip, would scatter the light, which was then detected by photomultipliers. The signals were processed by early industrial computers to map the location of defects. This defect map was fed downstream to the cutting bridge. Computer numerical control optimization software would then calculate the most efficient cutting pattern to avoid the defects while maximizing the yield of useful glass sizes. This intelligent cutting was a massive leap in efficiency, reducing waste and ensuring that only perfect glass was shipped to customers. The transition from manual bucking of glass sheets to automated vacuum lifters and robotic stackers further removed the human element from the dangerous heavy lifting, reducing injuries and allowing for the safe handling of the massive jumbo plates. Era of ion exchange and nanotechnology, 2000s to present. The dawn of the 21st century marked a definitive and irreversible schism in the history of materials science, particularly within the ancient domain of glass manufacturing. For millennia, glass was defined by its inherent fragility, serving as a static, passive barrier intended to admit light while excluding the elements. It was a material characterized by what it could not do. It could not bend without breaking, it could not bear structural loads without massive thickness, and it could not withstand ballistic impact without shattering into dangerous shards. However, from the year 2000 to the present day, the industry has undergone a radical and sophisticated transformation, moving from the production of passive transparent solids to the engineering of active, high-performance materials. This era, characterized by the mastery of ion exchange chemical strengthening and the integration of nanotechnology, has redefined glass as a structural, flexible, and ballistic material. This second part provides an exhaustive analysis of these developments, tracing the manufacturing evolution of alkali-aluminosilicate compositions for consumer electronics, the structural engineering of colossal architectural glazing, the atomic-level manipulation of electrochromic coatings, and the sintering of transparent ceramics for next-generation defense applications. We will explore how modern science has unlocked the quintessential nanotech material, pushing the boundaries of physics to create transparent armor lighter than steel and glass thin enough to fold like paper. Evolution of alkali-aluminosilicate sheet glass. The ubiquity of the modern smartphone is inextricably linked to the evolution of its primary interface, the cover glass. Prior to the mid-2000s, mobile device screens were predominantly shielded by plastic, PMMA, or weak soda-lime glass, materials prone to scratching, hazing, and shattering upon minor impact. The introduction of the capacitive touchscreen in the late 2000s necessitated a material that was not only optically pristine and highly transmissive to support vibrant displays, but also dielectric to enable touch sensitivity and capable of withstanding the rigors of daily handling, drops, and abrasion. This demand catalyzed the resurrection and refinement of alkali-aluminosilicate glass, a composition that would become the industry standard for high-strength optical covers. The transition from traditional soda-lime glass to alkali-aluminosilicate glass represented a fundamental shift in chemistry, designed specifically to facilitate chemical strengthening. Soda-lime glass, the material of common windows and beverage bottles, lacks the atomic structure necessary for deep chemical strengthening because its network is relatively tight and chemically stable in a way that resists ion mobility. In contrast, aluminosilicate compositions contain significant amounts of aluminum oxide, which opens up the silica network. The presence of aluminum creates charge deficits and interstitial sites that dramatically increase the mobility of alkali ions within the glass matrix. This structural porosity is the prerequisite for the modern ion exchange process, allowing larger ions to migrate deep into the surface. Leading this revolution was Corning Inc. with its Gorilla Glass, a brand that became synonymous with damage-resistant cover glass. The development of this material was not an overnight discovery, but a strategic refinement of ChemCore glass, a project originally explored in the 1960s under the internal name Project Muscle. ChemCore was initially intended for automotive windshields, but the market was not ready for the cost or the technology, leading to the project being shelved for decades. With the advent of the iPhone and subsequent smart devices, Corning resurrected these formulas. They utilized the fusion draw process, a manufacturing technique where molten glass overflows a V-shaped trough, known as an isopipe. The molten glass flows down both sides of the trough and fuses at the bottom in mid-air. This method ensures that the surface of the glass remains untouched by mechanical parts or molten tin, unlike the float glass process used for windows, minimizing the introduction of microscopic flaws that could act as failure initiation sites. The result is a pristine, fire-polished surface that requires no grinding or polishing, retaining its inherent theoretical strength. Concurrent with Corning's dominance, competitors arose to meet the insatiable demand of the global electronics market. AGC Inc., formerly Asahi Glass Co., introduced Dragon Trail, utilizing a similar Alkali-Aluminosilicate family, but manufacturing it via the float process. The float process involves floating molten glass on a bed of molten tin. While highly efficient for high-volume production of large sheets, the float process introduces a challenge. The glass side in contact with the tin side, can have a different chemical composition and stress profile compared to the air side, potentially complicating the chemical strengthening process. Schott AG also entered the fray with its Sensation brand, utilizing a lithium aluminosilicate composition. The inclusion of lithium, a smaller ion than sodium, allows for even more complex ion exchange scenarios, offering different balances of flexibility and hardness. This rivalry between these manufacturers has driven rapid generational improvements, with each iteration focusing on balancing two often opposing mechanical properties: drop resistance, fracture toughness, and surface hardness, surface hardening. Ion exchange process, engineering stress at the atomic level. The extraordinary strength of modern smartphone glass is achieved not through bulk thickness, which would render devices heavy and interfere with touch sensitivity, but through the deliberate introduction of compressive stress at the surface via the ion exchange process. This process is a prime example of diffusion physics applied at an industrial scale to alter material properties. The manufacturing of chemically strengthened glass begins with the immersion of the pristine aluminosilicate sheets into a bath of molten salt, typically potassium nitrate, heated to temperatures generally between 350 and 500 degrees Celsius. At this elevated temperature, the glass structure expands slightly, and the alkali ions within the glass matrix acquire enough thermal energy to become mobile. The crucial mechanism here is the stuffing effect. The smaller sodium ions naturally present in the glass composition diffuse out of the glass surface and into the salt bath. Simultaneously, they're replaced by larger potassium ions diffusing from the molten salt into the glass. Because the potassium ions have a significantly larger atomic radius than the sodium ions they replace, approximately 1.38 angstroms versus 1.02 angstroms, they require more physical space within the atomic lattice. As the glass is removed from the bath and cools, the lattice attempts to contract. However, the larger potassium ions, now wedged into the smaller vacancies left by the sodium, resist this contraction. This atomic overcrowding creates a layer of high compressive stress on the surface of the glass, effectively locking the surface in a state of compression. This compressive layer serves as a mechanical shield against fracture. Glass almost always fails under tension. A crack propagates when the atomic bonds at its tip are pulled apart. The deep compressive layer induced by the ion exchange process counteracts applied tension, such as bending or impact. Before a crack can open and spread, the applied force must first overcome this immense stored compression, which can reach values as high as 600 to 1,000 megapascals. The effectiveness of this protection is defined by two key parameters: compressive stress, CS, and depth of layer, DOL. Compressive stress dictates how much force the surface can withstand before a flaw opens, while the depth of layer determines how deep a scratch must be to penetrate through the protective compression zone and reach the vulnerable central tension region of the glass. If a flaw penetrates the DOL into the central tension zone, the stored tensile energy is released instantaneously, resulting in the catastrophic shattering often seen in dropped phones. While early generations of chemically strengthened glass had relatively shallow layers, modern variations employ complex multi-step exchange processes, sometimes involving mixed baths of sodium and potassium, or sequential baths of different concentrations to create deeper, graded stress profiles. These engineered profiles prevent flaws from penetrating into the central tension zone, even under severe impact. Nanotechnology and the rise of glass ceramics. As consumer demands for durability intensified, moving from merely preventing scratches to preventing shattering upon 2-meter drops onto concrete, the limits of amorphous glass began to be tested. The response from materials scientists was the development of glass ceramics, a hybrid material class that bridges the gap between the chaotic, random structure of glass and the ordered, rigid lattice of ceramics. The most prominent example of this technology in the consumer market is the ceramic shield, introduced by Apple in collaboration with Corning for the iPhone 12 and subsequent generations. Glass ceramics are manufactured through a sophisticated process of controlled crystallization. The material begins as a precursor glass, formed with specific nucleating agents such as titanium dioxide or zirconium oxide dissolved within the melt. This precursor glass is then subjected to a highly specific heat treatment regime. During this heating phase, the nucleating agents trigger the precipitation of tiny crystals within the amorphous glass matrix. In the case of ceramic shield, these are nanoceramic crystals, grown to be smaller than the wavelength of visible light. This sub-wavelength size is the critical innovation. In traditional ceramics, the crystal grains are large enough to scatter light, rendering the material opaque. Think of a white ceramic coffee mug. By keeping the crystallites on a nanoscale, they do not interact significantly with visible light waves, allowing the material to retain the high optical transparency required for a smartphone display cover while inheriting the superior mechanical properties of a ceramic. The mechanical advantage of this nanostructure lies in its ability to deflect and arrest crack energy. In a pure amorphous glass, a crack travels in a relatively straight line through the random network, cleaving bonds with little resistance. This is why glass is brittle. In a glass ceramic, the embedded nanocrystals act as obstacles. When a crack tip encounters a harder nanocrystal, it is forced to deflect, branch, or blunt. This tortuous crack path dissipates significantly more energy than a straight fracture, arresting propagation before it leads to failure. Furthermore, these materials typically undergo a dual ion exchange process, which reinforces the glass matrix surrounding the crystals. This creates a composite material where the crystals provide hardness and crack deflection, while the chemically strengthened matrix provides compressive resistance, offering up to 4 times the drop performance of traditional aluminosilicate glass. Bending reality, ultra-thin glass, UTG manufacturing. The most recent frontier in consumer electronics is the foldable display, which necessitated the development of a cover material that could withstand the seemingly impossible, bending to a radius of a few millimeters thousands of times without fracturing. This requirement gave rise to ultra-thin glass, a material that defies the intuitive rigidity of glass by leveraging the physics of thinness. The manufacturing of UTG, often as thin as 30 micrometers, roughly the thickness of a human hair, relies on extreme precision in the drawing process. Manufacturers like Schott and Corning utilize down draw and fusion draw methods, respectively, to produce these gossamer sheets. In the downdraw process, molten glass is pulled through a precision nozzle or slit by gravity and rollers, stretching it to the desired thinness while maintaining thickness uniformity. The fusion draw process is similarly advantageous because it produces a sheet with pristine surfaces that have not touched a mold or tin bath, reducing the population of surface flaws that could lead to fatigue failure. The flexibility of UTG is governed by the relationship between thickness and bending stress. Bending stress is directly proportional to the distance from the neutral axis, the center of the sheet, to the surface. As the thickness of a material decreases, the tensile stress on the outer surface during bending decreases proportionally. At 30 microns, glass behaves more like a stiff polymer than a brittle solid, capable of significant elastic deformation without reaching its fracture limit. However, thinness alone is insufficient. The surface must be virtually free of defects, as even a nanometer-scale flaw can act as a stress concentrator, leading to failure during repeated folding. To enhance durability and handling, UTG is often subjected to an intensifying process, a specialized chemical strengthening treatment tailored for thin substrates to impart a compressive layer without inducing warping. Furthermore, to protect the fragile glass from impact and to contain shards in the event of breakage, companies like Samsung inject a special material, typically a polymer or resin composite, into the glass structure or apply it as a coating. This creates a laminate system where the polymer provides impact absorption and protection, while the ultra-thin glass provides the smooth, hard touch interface and prevents the deep creasing common in purely plastic screens. This composite approach allows the stack to survive hundreds of thousands of fold cycles, termed tough yet tender by Samsung marketing, reflecting its dual nature of resilience and pliability. Skyline and the Smart Building, Advanced Architectural Glass. While the electronics industry focused on the microscopic strengthening of small screens, the architectural world pursued the macroscopic engineering of massive, transparent structures. The fundamental philosophy of building with glass shifted from using it as a mere infill material to employing it as a primary load-bearing structural element, capable of supporting roofs, resisting hurricane-force winds, and actively managing building energy loads. The demand for uninterrupted transparency in modern architecture, driven by flagship retail stores, airports, and luxury high-rises, drove the manufacturing of jumbo and super jumbo glass sizes. Standard architectural glass sheets traditionally topped out at around 6 meters in length. However, recent advancements in float lines and coating technologies now allow for the production of panels exceeding 3.2 meters by 12 meters, and in some specialized lines up to 20 meters in length. Manufacturing these behemoths requires specialized handling equipment, larger autoclaves for lamination, and furnaces capable of maintaining uniform temperature profiles over vast areas to prevent warping or residual stress imbalances. In structural glazing, these massive glass panels are not merely supported by a metal frame, they are the frame. Glass fins and beams are designed to bear the dead load of the facade and the dynamic loads of wind, snow, and seismic activity. This application requires a rigorous understanding of glass mechanics, particularly the concept of redundancy. Because glass is a brittle material that fails catastrophically without yield, structural glass components are invariably laminated. By bonding multiple layers of glass, plies, with high-strength ionoplast interlayers, such as Sentry glass, engineers ensure that if one ply fractures due to impact or inclusion, the remaining plies and the stiff interlayer can continue to support the load. This fail-safe engineering principle is evident in iconic structures like the Apple Store glass cubes. The Fifth Avenue cube, for instance, evolved from a structure with 90 glass panes to a simplified version with only 15 vast panels, seamlessly joined. The glass fins supporting the structure act as columns, transferring the weight of the roof and snow loads down to the foundation. This requires not just strong glass, but precise connection detailing where the glass meets metal fittings, ensuring that stress concentrations do not exceed the material's capacity. Similarly, the Grand Canyon Skywalk utilizes massive multi-ply laminated glass flooring units that are designed to support the weight of hundreds of visitors and withstand high wind uplift pressures, demonstrating the capacity of glass to serve as a primary structural floor. As buildings became more transparent, energy efficiency became a critical concern. Traditional double or triple glazing relies on gas, argon or krypton to insulate, but heat can still transfer through convection and conduction within the gas. The development of vacuum insulating glass, VIG, represents a quantum leap in thermal performance, attempting to replicate the insulating power of a thermos flask in a flat window format. A VIG unit consists of two panes of glass separated by a vacuum gap of only 0.1 to 0.3 millimeters. The elimination of gas in this gap effectively nullifies conductive and convective heat transfer between the panes, leaving radiation as the only transfer mechanism, which is mitigated by high-performance low-E coatings. This allows a VIG unit less than 10 millimeters thick to achieve insulation values, U values, comparable to a thick masonry wall or a triple glazed unit 3 times its thickness. However, creating and maintaining this vacuum presents immense mechanical challenges. The atmospheric pressure acting on the outside of the glass panes is approximately 10 tons per square meter. Without internal support, the two panes would instantly collapse into contact under this crushing weight, eliminating the vacuum gap. To prevent this, a grid of microscopic support pillars, spacers, is placed between the panes. The spacing and design of these pillars are a complex optimization problem involving thermal and mechanical physics. If the pillars are too far apart, the glass will bow inward and touch under atmospheric pressure, or the stress on the individual pillars will become so high that they crush the glass surface, Hertzian contact stress. If they are too close together, the pillars themselves act as thermal bridges, conducting heat from the warm pane to the cold pane, and reducing the overall insulation value of the window. The pillars, typically made of high-strength steel or ceramic and measuring roughly 0.5 millimeters in diameter, are spaced between 20 and 40 millimeters apart to balance these opposing forces. Research indicates that increasing spacing from 20 millimeters to 40 millimeters can reduce the number of thermal bridges significantly, but it quadruples the load on each individual pillar, requiring careful stress analysis to prevent indentation failure. The sealing of the VIG unit is equally critical. The vacuum must be held for decades against the relentless pressure of the atmosphere. Traditional seals used glass frit, a powdered glass paste that was melted to fuse the edges. However, the high temperatures required to melt the frit, around 450 degrees Celsius, can annul the tempered glass, reducing its strength and distorting its flatness. This has led to the adoption of advanced sealing techniques, such as laser sealing and low-temperature metal solders. Laser sealing allows for localized heating of the edge frit without affecting the temper of the main glass body, preserving the structural integrity required to withstand the pressure differential and thermal shock. Parallel to the development of static insulating technologies, smart glass technologies have introduced dynamic control over light and heat. Electrochromic glass, which can switch from transparent to tinted on demand, is manufactured using sophisticated vacuum deposition techniques similar to those used in semiconductor fabrication. This technology allows buildings to actively manage solar heat gain, reducing the load on HVAC systems and eliminating the need for mechanical blinds. The manufacturing process typically involves magneto-sputtering, a vacuum coating technique where high-energy plasma ejects atoms from a target material, such as tungsten or nickel, depositing them in thin, uniform layers onto the glass substrate. An electrochromic stack is essentially a transparent, multi-layered battery deposited directly on the glass. It generally consists of 5 layers: a transparent conductor, like indium tin oxide, ITO, an electrochromic electrode, often tungsten oxide, an ion conductor, electrolyte, a counter-electrode, storage layer, and a second transparent conductor. The operation of the glass relies on the physical migration of ions, typically lithium ions. When a low voltage is applied across the conductive layers, lithium ions migrate from the counter-electrode, storage layer, through the electrolyte and insert themselves into the tungsten oxide lattice. This intercalation process changes the oxidation state of the tungsten atoms, altering their electronic structure and causing the material to absorb light and turn dark, usually a deep blue tint. Reversing the voltage extracts the ions back into the storage layer, returning the glass to a transparent state. The precision required in manufacturing is extreme. Uniformity of the coating thickness across large architectural panes, up to 3 meters wide, must be controlled to the nanometer level to ensure consistent coloring and switching speeds, preventing the halo effect or uneven tinting. Next-gen armored and defense glass, the era of transparent ceramics. In the defense sector, the limitations of traditional laminated glass, specifically its immense weight and thickness required to stop modern ballistic threats, have driven a transition toward transparent ceramics. Materials such as aluminum oxynitride, ALON, and magnesium aluminate spinel, represent the apex of transparent armor technology, offering multi-hit capability at half the weight of legacy glass systems. Unlike glass, which is an amorphous solid formed by melting and cooling without crystallization, transparent ceramics are crystalline materials produced through advanced powder processing and sintering. The manufacturing begins with high-purity ceramic powders, aluminum, oxygen, and nitrogen for ALON, and magnesium aluminate spinel for spinel. These powders are formed into a green body, a chalk-like solid, using techniques such as cold isostatic pressing or slip casting. This stage is versatile, allowing for the creation of complex shapes like curved windows or hemispherical domes for missile seekers, shapes that are difficult to achieve with traditional glass grinding. The transformation from an opaque powder compact to a transparent window occurs during sintering. The green body is heated to high temperatures, often exceeding 1800 degrees Celsius, under pressure. This process, often involving hot isostatic pressing (HIP), is critical for eliminating porosity. In a ceramic, any microscopic pore acts as a light-scattering center, rendering the material opaque. By applying uniform gas pressure at high heat, the material is densified to near theoretical limits, removing voids and fusing the crystal grains together. The result is a polycrystalline material with the optical clarity of glass, but the mechanical properties of a sapphire gemstone. ALON, for instance, has a cubic crystal structure that is isotropic, meaning light travels through it at the same speed in all directions, preventing the birefraction, double refraction, that plagues other ceramics like alumina. This optical fidelity allows it to be used for high-precision sensor windows and laser rangefinders in addition to armor. The ballistic superiority of transparent ceramics over traditional glass lies in their hardness and fracture mechanics. ALON and spinel are significantly harder than borosilicate or soda-lime glass. When a high-velocity projectile, such as an armor-piercing round, strikes a transparent ceramic armor system, the extreme hardness of the ceramic face erodes and fractures the projectile upon impact. This dwell phase dissipates a massive amount of kinetic energy before the projectile can penetrate the layers below. Traditional glass armor relies on bulk and mass to stop bullets, often requiring thick, heavy laminates that degrade vehicle mobility and payload capacity. A ceramic-based system can achieve the same ballistic rating, for example, stopping a .50 caliber armor-piercing round at approximately half the weight and thickness of a traditional glass laminate. Furthermore, the polycrystalline structure of these ceramics offers superior crack management compared to the amorphous structure of glass. In traditional glass, a ballistic impact often causes long radiating cracks that can extend to the edges of the panel, obscuring vision and compromising the structural integrity of the entire window. Transparent ceramics, particularly when incorporated into composite laminates with polymers like polycarbonate and PMMA, exhibit a localized fracture pattern. The interlocking nature of the crystal grains and the damping properties of the polymer interlayers suppress the propagation of long-range cracks. This localization of damage is crucial for multi-hit capability. A vehicle window made of traditional glass might be rendered opaque or structurally unsound after a single hit, leaving the crew vulnerable to subsequent shots. An ALON or spinel window, however, retains visibility and structural integrity over the remaining surface area, allowing it to withstand successive impacts, a vital requirement for modern combat vehicles operating in hostile environments. The layered design of these systems, typically a ceramic strike face, a glass or polymer intermediate layer, and a polycarbonate spall shield, exploits the synergy of materials. The ceramic breaks the bullet, the intermediate layer absorbs the shock, and the backing catches the debris. Automotive and aviation complexity, motion and curvature. The transport sector has paralleled these advancements, driven by the dual needs of aerodynamics and aesthetics. The modern vehicle cockpit and aircraft fuselage demand glass that is not only strong, but also shaped into complex 3D curvatures that were previously impossible to manufacture efficiently. The production of complex curved glass for automotive windshields and dashboards relies primarily on two techniques: gravity bending and press bending. Gravity bending is the more traditional and cost-effective method. A flat glass sheet is placed over a mold frame and passed into a furnace. As the glass softens, gravity pulls it down into the shape of the mold. While effective for simple curves, this method is limited by physics. It relies solely on the weight of the glass and the heat profile. It struggles to create the sharp bends, deep sags, or complex saddle shapes, curvature in two axes, demanded by modern automotive designers for wraparound windshields. To achieve the complex geometries required for modern digital cockpits and aerodynamic exteriors, the industry has shifted toward press bending. In this process, the softened glass is mechanically forced into shape between a male and female mold inside the furnace. This allows for precise control over the curvature, enabling the production of shapes with tight tolerances that gravity alone could not achieve. This technology is essential for the integration of large curved displays in vehicle interiors, where a single piece of glass may cover the entire dashboard, integrating instrument clusters and infotainment screens into a seamless 3D surface. This often requires the glass to be chemically strengthened after bending to ensure it meets safety standards for head impact and airbag deployment. A notable application of advanced glass in automotive design is the Ford GT, which utilized a hybrid windshield made of Gorilla Glass. This windshield used a 3-layer laminate, an inner layer of chemically strengthened automotive-grade Gorilla Glass, a thermoplastic interlayer, and an outer layer of annealed soda-lime glass. This hybrid construction allowed the windshield to be 30% lighter and 25 to 50% thinner than traditional laminates, lowering the vehicle's center of gravity and improving handling while maintaining superior resistance to stone impact. In aviation, the challenge of curvature is compounded by the extreme environment of flight. Aircraft windshields must withstand the immense pressure differential between the pressurized cabin and the thin atmosphere at cruising altitude, all while enduring thermal shock from sub-zero external temperatures to heated internal conditions. Manufacturing these transparencies involves the lamination of multiple plies of chemically strengthened glass or stretched acrylic. The bending process for these thick laminates is slow and meticulous. Unlike automotive glass, which allows for some minor optical distortion in peripheral areas, aviation glass requires optical perfection for pilot visibility. The bending must be controlled to prevent lens effects or distortion that could misrepresent the position of objects outside the aircraft. Furthermore, aviation glass often incorporates conductive coatings for de-icing and anti-fogging. These coatings, typically made of thin layers of gold or indium tin oxide, ITO, function as resistive heaters. Applying these coatings to a curved surface requires precise control to ensure uniform thickness. Any variation in thickness leads to uneven heating, creating hot spots that can induce thermal stress and damage the laminate or the coating itself. The electrical bus bars that power these coatings must be robustly integrated into the edge of the laminate to withstand vibration and thermal cycling. The structural engineering of these windows is a critical safety discipline. The glass must be designed to hold the full cabin pressure even if one or more structural plies fail, relying on redundant layers and fail-safe mounting systems to protect the crew and passengers. The period from the year 2000 to the present has witnessed the maturation of glass as an engineered material. No longer defined solely by its transparency, glass has acquired the properties of metals and ceramics, strength, flexibility, and active responsiveness, while retaining its essential optical character. The trajectory of this evolution is clear: the convergence of chemical processing and nanotechnology. In consumer electronics, the ion exchange process and glass-ceramic nucleation have turned fragile screens into structural shields, capable of surviving drops that would have shattered previous generations. In architecture, the manipulation of vacuum physics and ion migration has turned windows into active thermal barriers and light management systems. In defense, the sintering of ceramic powders has created transparent armor that defies the weight-performance trade-offs of the past. And in transportation, advanced bending technologies have allowed glass to conform to the aerodynamic and aesthetic demands of the future. As manufacturing techniques like fusion draw and magnetron sputtering become more refined, and as our ability to manipulate material structure at the nanoscale deepens, the distinction between glass, ceramic, and functional device continues to blur. The glass age is not merely a marketing moniker, but a reflection of a material reality where glass has become the active interface between the human and the digital, the built environment and the elements, and the protected and the threat. Future advancements in self-healing glass and diamond-like coatings promise to further extend the capabilities of this versatile material, ensuring its centrality to technological progress for decades to come.